Right, awesome. We have Benjamin Jones from ASU, a former goalie, who's going to be presenting on ideals, SAR homomorphisms, and approximate identities. So, Ben, go right ahead whenever you're ready.
Thank you, Rolando. Yeah, I think I'll start with a theorem from the notes. This is theorem 14.3. At least part of theorem 14.3, the, the uh, main part of theorem 14.3, which says that if you have a star homomorphism between C star algebras, call it phi, and it's injective, then in fact, pi is isometry. So this this theorem is really telling us that from a purely algebraic perspective, the star homomorphism only involves the algebraic structure of the C star of the map pi. We actually get information about norm structure. And the proof
Oh, yeah.
allows us to use some of the technology we developed for, uh,
Actually.
yeah, hello.
Oh, sorry. Oh my gosh.
It's okay. Uh, So the proof allows us to use the technology we developed with positive elements of C-star algebras. The first step really is to see that we only need to know it's isometric on positive elements. The reason why is that the norm of pi of a squared, that's the norm of pi of a star pi of a by the C-star identity. Since pi is a star homomorphism, that's the norm of pi of a star a. And again, by the C-star identity, the norm of a star a is the norm of a squared. So if we know that the norm of pi of a star a is the norm of a star a, then we know that the norm of pi of a is the norm of a. And a generic positive element by a theorem from the last section is an element of the form a star a. So it suffices to prove that pi is an isometry on just the positive elements. Great. So let's choose an arbitrary positive element A. It's a previous theorem that the norm of pi of A is at most norm of A. So we already knew that pi is continuous in a contraction. So we'll suppose that the norm of pi of A is strictly less than the norm of A. So one thing we know about positive elements by definition is that their spectrum is contained in the real numbers. So spectrum of A, not just the real numbers, but the positive, the non-negative real numbers. So the spectrum of A is in this interval from 0 to infinity, but actually we have 0 to norm of A here. And we also, from our characterization of positive elements, we can see that pi of A is itself is positive for the same reason we have at the start of the proof. Pi of A is pi of square root of A, square root of A, square root of A is self-adjoint. So that's pi of square root of A star pi of square root of A. And in particular, this tells us that the spectrum pi of A is contained in the closed interval from 0 to norm of pi of A. And our assumption that the norm of pi of A is strictly less than the norm of A tells us that this interval is strictly contained in the interval from 0 to norm of A. So the strategy is to use functional calculus, construct an element from A whose image under pi is 0, and then use the fact that functional calculus is an isomorphism to show that the f, our function applied to A, actually is non-zero. And for that, we need an element of the spectrum of A which does not belong to the spectrum of pi of A. And so that element is the norm of A. The norm of A is in the spectrum of A, but not in the spectrum of pi of A. I'm sure you guys, before proving functional calculus, had to prove that the norm of A is in the spectrum of A, but just in case, here's a quick reason why the norm of A has to belong to the spectrum of A. Because by functional calculus, we have an isomorphism between C0 of the spectrum of A minus 0 and the C star algebra generated by A. And this isomorphism maps the identity function in C0 to the element A. And this isomorphism is isometric. So the norm of the identity function in C0 of this set has to be the norm of A. And the norm of the identity function is the supremum of the uh, the spectrum of A minus 0. So in particular, if the norm of A wasn't in the spectrum of A, and the spectrum of A would since it's compact, would have to be contained in a smaller closed interval. But we know that can't be the case because then the norm of the identity in this map would be smaller than the norm of A. Okay, so we have an element of the spectrum of A which does not belong to the spectrum of pi of A. And we'll construct any function which is 0 on the spectrum of pi of A, but non-zero on the spectrum of A. So for example, we could say if this is norm of pi of A, and this is norm of A, and we could define a function f, which is 0 on the elements from 0 to norm of pi of A, and it's 1 on norm of A, and if we wanted to be explicit, we could just say it's this line segment in between. 6 is 1. So f, the image of this interval, is 0, and f evaluated at norm of A is 1. Then functional calculus is an isomorphism. And f as an element of C0 from of the spectrum of A minus 0 is non-zero. So since functional calculus is an isomorphism, f of A is non-zero. However, f of pi of A is pi of f of A. This is something we proved in the section on functional calculus. And f of pi of A, when we're applying functional calculus, but viewing f as a function in C0 of the spectrum of pi of A minus 0. So viewing f as a function in that space, f restricted to this spectrum of pi of A minus 0 is 0. So that means f of pi of A is 0. And that's pi of f of A. So we have a non-zero element f of A which maps to 0 under pi. So this contradicts the injectivity of pi. We arrived here by assuming that the norm of pi of A was strictly less than the norm of A. So we must have that the norm of pi of A is equal to the norm of A. Remember, we already knew that the norm of pi of A had to be at most the norm of A. So now we know that any injective star homomorphism you have between C-star algebras, you actually have that it's not only continuous, but in isometry if it's injective. And there's a nice corollary we get from this. So in fact, if we have a homomorphism pi from A to B, which is injective, A and B are C-star algebras, then the image of A is a C-star algebra. And this is really useful because in an abstract algebra class, you wouldn't think twice about, the image of a group homomorphism being a group. But with C-star algebras, we do have to think twice because we have the extra requirement that we have a norm for which the C-star algebra is complete and the C-star identity, etc. The properties of uh, the norm except for completeness. So the properties of the norm except for completeness follow since pi is a homomorphism and continuous. And contractive. Except completeness. So for completeness, we will use the fact that pi is an it is injective. So it's an isometry. So this is a general fact about metric spaces where if you have an isometry from a complete metric space, then its image has to be complete. But just to be thorough, I'll write the proof. So we want to prove that the image is closed. Since B is closed, since B is complete, if the image is closed, then the image is complete. So if the limit of, say, pi of an, some arbitrary sequence in the image of A, is B, then the sequence pi of an is Cauchy, and pi is an isometry, so pi doesn't change the distances between the ans. So that means the sequence an is Cauchy. So limit of the ans exists, and say it's equal to some A. Then pi is an isometry, so it's continuous. So pi of A is the limit of pi of the ans. And pi of A, of course, is in the image of A. So the image is closed, and since B is complete, the image is complete. So in fact, we have a C-star algebra. Now, in your notes, if you in your notes, when you go and read the section, you'll see that you actually don't need the star homomorphism to be injective in order for the image to be a C-star algebra. And that's because we have something like the first isomorphism theorem for C-star algebras too. So I will, uh, so that's what I'm going to cover next. And that's going to allow us to extend this corollary to any arbitrary homomorphism. So this is theorem 4.11. It says that if you have a C-star algebra and some ideal, which is my convention for when I just say ideal is that it's closed and two-sided. So if you have some C-star algebra and an ideal, then the quotient of A by the ideal is a C-star algebra. And the norm on that C-star algebra is given by saying that the norm of the coset for some x is the infimum over all elements in your ideal of the norm of x plus that element. So general functional analysis gives you that A mod J is at least a Banach star algebra. Oh, A mod J is at least a Banach algebra, and then if it's closed under star, I think you need closed under star, then you get that it's a Banach star algebra. So the actual difficulty here is to verify the C-star identity, and the proof is using approximate identities, but I won't be going over the proof. However, I will talk about approximate identities soon. So, okay, and as a corollary to this theorem 4.11, we can extend the previous corollary and get that the image of any C-star algebra under any homomorphism is a C-star algebra. I should I'll say any star homomorphism between C-star algebras I has the image the image is a C-star algebra. The proof, well, for the proof, we want to uh, instead of using pi, use the injective homomorphism pi factors through. So pi factors through, say, pi tilde going from A mod the kernel of pi into B. So in other words, and it factors by the quotient map. So to be precise, pi of A, pi tilde of A, sorry, I should say pi tilde of A plus the kernel, so the coset for A, is defined to be pi of A. And pi tilde is injective. It's injective by construction. If it wasn't, then there would be an element A, which is not in the kernel for which pi of A is 0. That can't happen. Kernel of pi is a closed two-sided ideal. And not that this theorem says it, but it says that you need it, but it's also star closed, which is easy to check in this specific case for the kernel of pi. And because of that, we have a injective star homomorphism between C-star algebras. A mod kernel is a C-star algebra by theorem 4.11. And so by previous corollary, we get that the image of pi tilde, which is the same as the image of pi, is a C-star algebra. So in any circumstance where you have a homomorphism between C-star algebras, which is just uh, a purely algebraic requirement, you don't have to worry about whether the image of that homomorphism is still a C-star algebra. Okay, so like I said, the proof of theorem 4.11 uses this tool called an approximate identity. So now I'm going to tell you what an approximate identity is. This is definition 4.1. It's an approximate identity and I like to say approximate unit. So if I say that, that's what I mean. So it's say in a C-star algebra, call it A. It's a net. So remember, a net is kind of like a sequence, except your elements are indexed by some directed set. So it's a net, call it E lambda, call the elements E lambda, for lambda in some directed set S. And for us, you can require these nets to satisfy various similar hypotheses, but these are the ones we'll use. So the first is we'll say that the net sort of respects the order structure in the directed set. So if you have some indices, gamma and lambda, and say gamma is less than lambda, then E gamma is less than E lambda. And actually, importantly, we can also, I should say we can require these to be positive, all of them to be positive. So I'll say 0 is less than E gamma less than E lambda. Also, we can require that the norm of each of the E lambdas is at most 1. And finally, and maybe most importantly, we can require the limit of this of the net E lambda A is equal to A, which is the same as it's written in your notes as the limit of the norm of E lambda A minus A is 0. And we can have this happen, in fact, for all elements of A. So approximate identities are useful tools for when your C-star algebra doesn't have a unit. You can think, I know in your notes you have one exercise where you have to come up with an approximate unit for the compacts. And you can also think for commutative C-star algebras, what would this look like? Sorry, my computer is saying my internet is down. Can you hear me?
Yeah, we can hear you.
Okay, uh, that's good. Thanks. Okay, hopefully that's not an issue, because normally when it says that it's correct. But okay. Um, right. So in your notes, you have to come up with an approximate identity for the compacts. But you can think of what this means for a commutative C-star algebra, C0 of x. You can just imagine maybe some positive bump functions approaching pointwise the function which is just 1 at every input. And that would be uh, more or less approximate example of an approximate unit. Okay, so now there's a really technical theorem, but uh, I think the proof is pretty cool. This is theorem 4.4. And it tells you that not only does every C-star algebra have an approximate identity, but any C-star algebra with and say any ideal in that C-star algebra has an approximate identity you can select within that ideal that's an approximate identity for the elements in that ideal. So let me write this out. Say A is a C-star algebra. And this ideal, closed two-sided ideal, J, sits inside A. So there's some net. Again, I'll call it E lambda. And this net is an approximate identity not necessarily for A, but for all the elements in J. So we have 1 and 2 hold and 3 holds for all elements A not necessarily belong to the C-star algebra, but to the ideal. And you select this ideal to be A itself. And you get an approximate identity for every C-star algebra A. I won't go over the proof because that would take too long, but I can regurgitate the idea of the proof. So in the proof in your notes, this directed set S is constructed as the collection of all finite subsets of self-adjoint elements belonging to J, ordered by inclusion. And then to construct the E lambdas, you sum up the squares of the elements of those elements and then evaluate at some particularly chosen function using functional calculus. You get all of the properties 1, 2, and 3 that you require for the approximate identity. So it's a really nice application of functional calculus. So approximate identities allow us to do a lot of really important things that we would maybe only necessarily expect to do with unidal C-star algebras. So here's a lemma. This is lemma 4.8. So this lemma will use approximate identities. It says that if J is an ideal in your C-star algebra, here, oh yeah, just J is an ideal. Norm closed two-sided, that's what I always mean by ideal. Then J is closed under taking adjoints. So I'll write that as J star is equal to J. Okay, so Let's prove this. Now, we don't necessarily know that J is a C-star algebra if we don't necessarily know yet that J is a C-star algebra if we don't know that it's closed under taking adjoints. But we can get a C-star algebra by taking the intersection of J with J star. So define B to be that intersection. J intersects J star. Now, if J is not the trivial ideal, so first of all, B contains 0, and J is closed under addition, J star is closed under addition, and J is closed under multiplication, so J star is closed under multiplication. And B inherits the C-star identity from A, so B is a C-star algebra. So it's a C-star algebra, C-star subalgebra of A. And one nice thing about B is that if X belongs to this ideal J, say, then X star belongs to B because J is an ideal, so X times anything belongs to J. And so X star belongs to J, and X star, take the star of that, that's just equal to X star. And since X star is in J, this is also in J star. Also, you have, just by replacing X with its adjoint, X star X is in B. So now we'll select an approximate identity for B. Okay, then, for example, X star minus X star E lambda still belongs to B because all of the constituents belong to B. And then we do the following calculation. We compute the limit of the norm of X star minus X star E lambda. See, X star belongs so X star belongs to J star and X star E lambda. So E lambda belongs to J and J star. Since E lambda belongs to J star and J star is closed under multiplication, X star E lambda belongs to J star. But J is an ideal and E lambda belongs to J, since E lambda belongs to B. So X star E lambda belongs to J as well. So actually, x star e lambda belongs to B. So in particular, it belongs to J. So we're going to compute this limit, and the reason why we're doing this is because these x star e lambdas actually do belong to J. So we want to see how far away is x star from J. And if we prove that it's a distance 0 from J, then if we prove that this limit is 0, then x star is approximated by elements of J, and since J is closed, x star had to belong to J. And since x is an arbitrary element of J, that proves that J is equal to J star. So how do we compute this limit? Well, like a lot of tricks with that we see in this section, it's with the C star identity. First, I'll square this norm. And everything I said about computing this limit is still true if I just squared the norm. But now I can apply the C star identity. So this is the limit of the following expression, say x minus xe lambda times x star minus x star e lambda. And here we're using the fact that the e lambda is self-adjoint since it's positive. Then you expand this, and what do you get? We get 4 terms. Um, oh, I was wondering what was going on because I was looking in my notes and things were in the wrong order. So I have to remember that when I take the adjoint, I also have to swap the order of the products. And I didn't do that. So I take the adjoint in the first factor and I get e lambda x, not x e lambda. But since e lambda is self-adjoint again, I just have an e lambda. Okay, so now I compute this norm. There we go. Okay, and I can estimate using my triangle inequality, etc. So we can, and then for the right two terms, we can factor out an e lambda from the right. Okay, so remember that the norms of the e lambda are at most 1, and also e lambda is an approximate identity for B, and that x star belongs to B. So both of these norms go to 0. So this limit is 0. So the limit of x star minus x star e lambda is 0. So x star belongs to the closure of J, but that's equal to J. Closure of J because these elements x star e lambda, like I said before, do belong to J. Um, yeah. Okay. And because of this lemma, so we have ideals are now, we know that all closed two-sided ideals are actually closed undertaking adjoints. So J is a closed subset of a C-star algebra. It's automatically complete. And we inherit the C-star identity from the ambient C-star algebra. So we actually have that every closed two-sided ideal of a C-star algebra is a C-star algebra. Again, this is one of those things that in an abstract algebra class, you wouldn't think twice about whether a normal subgroup of a group is a group or whether an ideal for a ring is still a ring. But this is something we have to check with C-star algebras. It's not necessarily obvious. And the nice thing about C-star algebras is that, you know, we can keep this mentality from that we have from abstract algebra. Okay. So that's one nice application of uh, of approximate identities. And since I have 5 minutes, I'll allude to another nice application that's in your notes. And it's another useful property of closed two-sided ideals. So this is a definition from section 4 in your notes. I fortunately didn't the number down, but if you have a C-star subalgebra of say A, then we call B hereditary. If for all, say, positive elements A and B, such that A is less than B, and say this element B belongs to the C-star subalgebra, we in fact have that A belongs also to the C-star subalgebra. And in your notes, you actually, you can see the, it, the notes actually talk about how this is hereditary subalgebras are in one-to-one correspondence with one-sided ideals. But I
Sorry, do you
won't.
mean A is in B, the C star subalgebra?
Yes, yeah, thank you. Oh, so I should say, yeah, yeah, yeah. I guess I didn't write that for the premise, A has to be in A, but it should be clear from context. So yeah, the conclusion is A is in B. In your notes, it's mentioned that these are in one-to-one correspondence with one-sided ideals, but I won't talk about that. But I encourage you to take a look at that. One example is you take a projection and take a corner, take the set of all elements that look like PAP for some projection P. Then you have this theorem. It's theorem 4.19, but I'm only mentioning like one half of it. It says that a C star subalgebra B of A is hereditary if, say, for all elements A in your C star algebra and say B and B prime in your subalgebra, B, A, B prime belongs to B. So in particular, so I guess a corollary of this, every closed two-sided ideal, because you think B is a closed two-sided ideal, then indeed EAB always belongs to that ideal. So as a corollary of this, you get that J is hereditary. So that's another useful fact to know about ideals, and that's what I'll stop with since I'm out of time. Does anyone have any questions? Oh, wait. I'm supposed to stop the recording.